This is video 11, girls, of our walkthrough for topic 1 in Unit 4, our notice for integration. We're on page 29 and we're talking about Simpson's rule. Now, you may remember back in methods talking about something called the trapezoidal rule, which is an example of a numerical method of integration. Basically taking a function and using strips in the shape of trapeziums to find the area under a curve. Take strips that are the same width, trapeziums, add up the area of each of the trapeziums and give the total area under the function. In a similar way, there's what we're about to talk about, which is called Simpson's rule. Now, Simpson's rule doesn't break strips under a function into trapeziums, but it does something similar. What it does is it takes 3 points on a function at a time. Now, any 3 points anywhere can be connected by a parabola. So Simpson's rule uses parabolic approximation to determine the area under a curve. You take 3 points and find a parabola between them. Now, that parabola there can then be divided into 2 evenly spaced strips, as long as the 3 points are evenly spaced between them. Now, take 3 points, find one parabola, and take the area underneath and divide it into 2 strips. That means for Simpson's rule to work, there must always be an even number of strips. 2 strips, 4 strips, 6 strips, etc., etc. Can't be an odd number of strips. Now, the way that it works is, well, there's a lovely derivation. Basically, the rule for Simpson's, finding the area under the curve according to Simpson's rules, comes down to this. It equals b minus a for a start. What's b and what's a? Well, b are the extreme lengths of your function along the x-axis. So b minus a represents the length of basically the whole thing that you're trying to find. Divide that by 3n. Where does the 3 come from? Doesn't matter. N represents the number of strips that you're dividing your area into. Again, it must be an even number. And then you multiply that by n's plus 4 times odds plus 2 times evens, where n's, odds, and evens represent lengths of strips the area is cut into, n being the number of strips. For example, if I was to take this function here, y is equal to fx, and divide it so that I make lengths. So the first strip is between x's equal to x0 and x1. That length x1 represents an end length. x1, on the other hand, represents an odd length, as x2 would represent an even length. Now at the other end of my strip, xn, which is the end length at the other end, that again represents an end length. So it might be an even number, n, but it's an n length anyway, so it's one of the n's. You take the lengths which are odds, like x1, x3, x7, add them up times by 4. You take the lengths that are evens, like x2, x4, x6, add them up and multiply that by 2. Add it all up together, you get an approximation of the area that you're trying to find. Let's use this idea on this shape at the bottom of page 29. Now, what have we got for a start? We're told that each of these strips are at 10 meter intervals. So between this 14 and this 18 length, there's 10 meters. And there's 1, 2, 3, 4, 5, 6, 7, 8 lengths altogether. So the whole thing from A down here to B down here is a length of 80. So B minus A is 80. Okay? So, area for a start is b minus a divided by 3n. We have n's plus 4 odds plus 2 evens. Okay, before I go any further, let me start naming my lengths here. So I'll call this length here, which is 14, is f0, f1, f2, f3, f4, f5, f6, f7, and this 7 6 again, f7, and this length, which would be f8, well, it's not f8, it's actually f of the n. It's an n. Now, by numbering that, I know which are the odd lengths, which are the n lengths. So, back to my area, which is approximately equal to this. Okay, b minus a for a start. Well, b minus a is the length of the whole thing, which we already worked out is 8 strips that are 10 meters wide, so that is 80. I'm going to divide that by 3n. What's n? N is the number of strips, which I already know is equal to 10. Okay, what are the n lengths? Okay, well, there's this length f0, which is 14. And I'm going to add that to the outer n down here, which is this much. How much is that? Well, f7 was 25, but this bit at the end is 0. Makes sense? Now I'm going to go add that to 4 times the odd lengths. What are the odd lengths? Well, that would be f1, f3, etc., etc. So that is 4 times 18, which is f1. Add that to 15, which is f3. Add that to f5, which is 28. And add that to f7, which is 25. Plus 2 times the evens, which would be f2, f4, etc. f2 is 12, f4 is 20, f6 is 28, and the f8 is not f8 at all, it's the end length. There's always going to be a greater number of odd lengths than there will be even lengths. Now, if I simplify that, 8 divided by 10 is 8, so that will be 8 on 3. 14 plus 0 is 14. 4 by 18 plus 15 plus 20 plus 25 is 344, I'm thinking. And 12 plus 20 plus 28 times that by 2 is 120. Now, put all that together, I get 1274.67. Now, is there a unit to put on this? Well, everything that was mentioned so far was in meters, and this is finding an area, so the unit is meters squared. Now, this was easy enough to do because the lengths that I needed, the lengths of the ends and the odds and the evens, are all given to us in this case. And we knew the width, we knew everything about it. It was just a matter of taking the lengths and putting them down. Now, when you're given a function, like on the next page, you have to find those lengths for yourself. Use Simpson's rule with 10 strips to approximate the area under the curve 4 on 1 plus x squared between 1 and 0 with respect to x. Well, alright. Well, we need a w to begin with. Now, what is w? W is this b minus a divided by 3n. Oh, sorry, it's, well, w is b minus a divided by n, so it's basically the width of each band. Later on, we take that width and we divide it by 3 again in the function. But to start with, the width of each, what is it? Well, for b and a, we look to what we're integrating between. That is 1 and 0. So 1 minus 0. And we're dividing it into how many strips? 10. So 1 minus 0 divided by 10 is 0.1. So the width of each strip is 0.1. So between the first value of x and the last, there's 0.1 between. Now, how do I find the lengths that I'm interested in? Well, we don't need to find the integral of 4 on 1 plus x squared. By putting values of x into that function, we already know what the values for y would be. So now the idea is, okay, I need some values. N values, odd values, even values. Starting with f0. Now where does f0 occur? When x is equal to 0 at the start of my domain. So the idea is I'm going to take 0 and put it into the function. So it's f0, which would be 4 divided by 1 plus 0 squared. 1 plus 0 squared, which would just leave you with 4. Alright? Now, the next bit, f1, would be when x is equal to 0 plus 0.1. Okay? 0.1 being the width. So 0 plus 0.1 would be 0.1. And to find that value of fx, I sub that value of 0.1 into my function. 4 divided by 1 plus 0.1, 0.1 squared. Now if you put that in your calculator, you get 3.9604. And even by this stage, my eyes are starting to glaze over, because that means I'm then going to have to go to the next one, which would be f2, and put in a value of x is. So I've got 0.1 and another 0.1, that would be 0.2. Now I'm going to have to put 0.2 into the function again. 4 divided by 1 plus 0.2 squared. Now my calculator says that's equal to 3.8462. Gosh, surely there's an easy way to do all this. Yes, sisters, there is. We can just get our calculator and find all of those values. So, here's what we do. Go to our calculator and go to y equals. Anything else that we had previously, we can get rid of for now. So clear, clear, clear. So I want to put the original function, which is 4 divided by, in brackets would be best, 1 plus x squared. Because x squared. Now I would like to know values for y when I change my values for x for this. So, and what I do is I find those values in my table, which I'll get to in a moment. But before I get to the table, go to second function and window to get to table set. Now this asks us where we want to start our values of x from. Well, we do want to start from 0, so that's good. So press enter for that, but then it asks for change in the table. What do we want the values of x to change by? Well, we know we want to change it by w, which is 0.1. So we go 0.1. And then it's a matter of putting those values now into my function. So now that I've set up my table, go to second function and graph to get to the table. And then you'll see values for our various values for x, starting with 0 and 0.1, 0.2, etc., etc., all the way up to 1, and their accompanying values for y1. Now that means those ones, and I already knew the first one was 4, and then 3.9604, and then 3.864, all those other values are the ones that I'm interested in. So, rather than having to go through laboriously finding all of those other things, I can write down the values for F2, F3, so on and so on and so on, which I'll now do back in my notice. And there you have it, using the GC, without having to plug in multitude of values, I can work out what my lengths are going to be for this particular function, starting with f0, which is an end, and finishing with f10, which is the other end. f1, f3, f5, f7, and f9 are the odds, and f2, f4, f6, and f8 are the evens. And again, I need all of those ones to work out the area. So the next thing is to add up the ends, the odds, and the evens. I might pause and do that as well. So, taking the end, which is f0, f10, that's 4 plus 2 is 6. All the odds, which is f1, f3, f5, f7, f9. Add them up, that's 15.7244. And add up the evens, f2, f4, f6, f8, 12.6747. So now we're ready for the area, which is W divided by 3. W divided by 3. And the W, remember, is B minus A divided by N. So W divided by 3. It's the N's plus 4 times the odds plus 2 times the evens. Odds being the sum of all the odd lengths, evens being the sum of even lengths, and ends being the sum of the 2 end lengths. So let's put in what we know. So W is the width of each strip, which is 0.1 divided by 3. The sum of the end was 6. The sum of the odds, well, it's 4 times the odds, which is 4 by 15.7244 plus 2 times the evens, which is 12.6747. Okay, grand total, that comes to about 3.14 units squared. Simple. Easy, huh? Yes. Remembering that the number of strips must be even. There were 10 strips there, that was even. In the next one, let's make some comparison about depending on the number of strips I use for this example. 3x squared integrating between the values of 2 and 6 dx. 4 strips and 10 strips. Okay, I might pause and just go to this, remembering, if you will, how I find those strip lengths. I need to put my function into my y equals my calculator. I change around with my table set, and then I go to the table second function graph to find those particular values. This is what I get for n strips. N. So for n is equal to 4, what's w, the width, going to be equal to? So I take my b and my a values from which I'm integrating between, which is 6 and 2. So if I go 6, take 2, and divide that by 4, the number of strips, it equals 1. So my first value, my first length, is starting at x is equal to. I sub that into my function, which is 3 by x squared. So that's 3 by 2 squared, which is 3 by 4, which is 12. And the next one, f1, would be 2 plus 1, which is 3. X is equal to 3. Sub that into my function, I get 27. The next one, f2, is 3 plus 1, which is 4. Sub that in, I get 28, etc., etc., etc. So, by doing that and numbering them and naming it F0, 1, 2, 3, and 4, I can tell which ones are my evens and my odds, etc. So, again, taking the odds, which are 12 and 108, add them up. I add to that 4 times the odds, which would be F1, F3, 27 plus 75, and 2 times the evens, which in this case would only be 48. F4 is not included amongst the evens because that's an odd length. Sorry, that's an n length, which I've already included. So, adding all that up together, I get a value of 208 units squared, remembering it's an area. Now let's compare that to when we take it into 10 strips. So again, what's the width going to be? Well, it's going to be 6 minus 2 again, but this time divided by 10. So that would be 4 divided by 10, that would be 0.4. So in this case, instead of going up in ones, I've got to go up in 0.4s. Yuck. Always good to have your calculator handy to do that. This is how I think it ends up for 10 strips. So this time I'm starting at x is equal to 2, so that's our f0, and going up to 0.4, so we go from 2 to 2.4 to 2.8 to 3.2, etc., etc., etc. So quickly I gave up on all that and just went to my calculator and found those particular values. Being important though is to number them off f0, f1, f2, etc., so we can find which ones are the odd strips and evens, etc. So how do I find the area? I need to take, again, the width and divide it by 3, and then ends plus 4 odds and evens. Now the width in this case is 0.4. Still got to divide by 3. Times that by adding the ends up together, which is 12 at the beginning and 108 at the end. 4 times the odds, Now the odds are F1, F3, F5, etc. So 17.28 plus 30.72 plus 48, etc., etc., etc. Plus 2 times the evens, which would be F2, F4, so on and so on. So that means 2 times F2, which is 23.52, plus F4, which is 38.88, etc., etc. Again, there being less even strips than there are odd strips. Now, if you put all of that in your calculator, it turns out to be, oh my goodness, 208 units squared. Pretty much the same area under the function, same function between 2 and 4, depending on what the number of strips were. If you had just 2 strips, sure, it might be a little less accurate than what you have here. But in this case, even 4 strips and 10 strips tends to work out the same. Alright, that's it for Simpson's rule. Girls, thanks. We've only got one last little bit to talk about as far as applications of functions and as per Quacker syllabus. So, our next video, which should be video number, will be video number 12, should be the last one. Alright, thanks girls. See ya.